Definition of direction cosines. Welcome, everyone. Let's begin our lesson on the definition of direction cosines. To start, I want you to think back to what you learned in two-dimensional geometry. You'll remember that when we want to describe how much a line is tilted or its inclination, we often use a single value called the slope. It's a very efficient way to tell us the steepness of a line on a flat plane. However, as we move into the study of three-dimensional space, we run into a bit of a challenge. A single value like slope is simply insufficient to describe the orientation of a line in 3D. This is because, unlike a flat plane, a line in 3D space can tilt in multiple directions across three different axes. The x, the y, and the z1 number just can't capture all that movement. So, how do we fix this? To solve this problem and provide a complete description of a line's orientation, we use a concept called direction cosines. In the next few slides, we will break down exactly how these are calculated and how they work. Understanding the concept. Imagine a line, which we'll call L, starting right at the origin, point O, which has the coordinates 0, 0, 0, and then extending out into our three-dimensional coordinate system. As this line stretches out into space, it isn't just floating randomly. It's going to form specific, measurable angles with the positive directions of the x-axis, the y-axis, and the z-axis. Now that we've established why a single slope isn't enough to describe orientation in 3D space, let's visualize what we are actually working with. Keep this image in your mind, because in the next slide, we are going to give these specific angles their own mathematical names. Step-by-step breakdown. Now that we have a mental picture of our line extending from the origin into 3D space, let's break down how we actually measure its orientation. In this first step, we define what we call the direction angles. Imagine our line, which we'll call L, stretching out into the coordinate axes. To describe exactly how it's tilted, we look at the angles it forms with each of the three axes. First, we look at the angle it makes with the positive x-axis, and we'll label this angle alpha. Next, we look at the angle it makes with the positive y-axis, which we'll call beta. And finally, we look at the angle it makes with the positive z-axis, which we'll denote as gamma. It is very important to remember that these three specific angles, alpha, beta, and gamma, are collectively known as the direction angles of the line L. Keep these angles in mind, because in the next slide, we are going to take the cosines of these angles to find our direction cosines. Step-by-step breakdown continued. Now that we have identified our three direction angles, alpha, beta, and gamma, from the previous slide, let's move on to step 2, where we actually define the direction cosines. As the name suggests, the direction cosines are simply the cosines of those specific angles we just discussed. To make our mathematical notation cleaner and easier to work with, mathematicians typically represent these three values using the lowercase letters L, M, and N specifically. We define L as the cosine of alpha, M as the cosine of beta, and N as the cosine of gamma. By calculating these three values, we create a set written as L, M, N, which acts like a unique fingerprint. This set uniquely describes exactly which direction the line is pointing in three-dimensional space. In the next slide, I'll give you a real-world analogy involving a laser pointer to help you visualize how these values actually work in practice. Real-world analogy. Now, I know that all these abstract angles and axes might feel a bit disconnected from reality, so let's use a real-world analogy to make this concept more tangible. Imagine you are standing in the corner of a room, holding a laser pointer right at the origin point, where the floor and two walls meet. To help us visualize our coordinate system, think of the lines where the floor meets the walls as our x and y axes, and the vertical corner where the two walls meet as our z-axis. As you move the laser pointer around, it points in a specific direction in 3D space. If you tilt the pointer, it creates three distinct angles. The angle it makes with the first floor wall intersection, which we call the x-axis, is alpha. The angle it makes with the second floor wall intersection, our y-axis, is beta. And finally, the angle it makes with that vertical corner, the z-axis, is gamma. Now, here is the key part. Just as we saw in the previous slides, we aren't just interested in the angles themselves, but in their cosines. The values of cosine alpha, cosine beta, and cosine gamma essentially act like a set of directional coordinates. They tell us exactly how much the laser is pointing along each axis, uniquely defining its direction in the room. This leads us perfectly into our next slide, where we will see how to apply this using a concrete numerical example. Illustrative example. Now that we have understood the theory and the concept behind direction cosines, let's put this knowledge into practice with an illustrative example. Suppose we have a directed line, let's call it L, that passes through the origin. We are given specific information about its orientation. It makes an angle of 60 degrees with the x-axis, 45 degrees with the y-axis, and 60 degrees with the z-axis. Our task is to use these angles to find the direction cosines of this line. This will allow us to see exactly how we transition from angles to the values of L, M, and N that we discussed in the previous slides. Illustrative example, continued. To find the direction cosines, we will follow a clear, step-by-step process. Our first step is to identify the direction angles from the information provided in the scenario. Looking back at our problem, we are given three specific angles. We have alpha equals 60 degrees, beta equals 45 degrees, and gamma equals 60 degrees. Now that we have the problem statement, let's move into the solution phase. We'll use these three angles as the foundation for our next calculation in the following slide. Illustrative example, continued. Now that we have identified our direction angles from the previous slide, we move on to the second step of our solution, which is to calculate the cosine of each of those angles. First, let's look at the x-axis. We take the cosine of alpha, which is the cosine of 60 degrees, and that gives us 1/2. Next, we move to the y-axis. We find the cosine of beta, which is the cosine of 45 degrees, resulting in 1 over the square root of 2. Finally, for the z-axis, we calculate the cosine of gamma. Since gamma is also 60 degrees, the cosine of 60 degrees is again 1/2. Once we have these three values, we will be ready to state our final set of direction cosines in the next slide. Illustrative example, continued. Now that we have calculated the individual cosine values for each axis in the previous step, we have reached the final part of our solution. For step 3, we simply need to state our final direction cosines. By grouping our results for L, M, and N together, we can conclude that the direction cosines of the line L are 1/2, 1 over the square root of 2, and 1/2. This triplet of values now provides us with the complete orientation of our line in three-dimensional space. In the next slide, we will wrap up this lesson by looking at the key takeaways and a very important mathematical identity you should always remember. Key takeaways. All right, we have reached the end of our lesson, so let's take a moment to consolidate everything we have learned today. I want you to focus on these three key takeaways as they summarize the entire concept of direction cosines. First, let's revisit the direction angles. Remember, these are not the cosines themselves, but the actual angles, alpha, beta, and gamma, that our line forms with the positive x, y, and z axes respectively. Think of these as the tilt measurements in each dimension. Second, we have the direction cosines. As we saw in our step-by-step breakdown earlier, these are simply the cosine values of those angles. We represent them using the lowercase letters L, M, and N, where L equals cosine alpha, M equals cosine beta, and N equals cosine gamma. This set of three values is what uniquely tells us exactly which way the line is pointing in 3D space. Finally, there is a very important mathematical identity you must remember. It is a fundamental property that the sum of the squares of these direction cosines is always equal to 1. In mathematical terms, that is L squared plus M squared plus N squared equals 1. Or, if you prefer to look at it in terms of the original angles, cosine alpha squared plus cosine beta squared plus cosine gamma squared equals 1. This property is a great way to check your work. If your calculated values don't satisfy this equation, you'll know something went wrong in your calculations. Now, before we finish, let's look at a few common pitfalls to avoid so you don't lose marks on your exams. Common mistakes to avoid. Now, as we wrap up this lesson, I want to highlight a few common pitfalls. Even if you understand the concept, it is very easy to make small errors that can lead to the wrong answer in an exam. First, be careful not to confuse the angles with the cosines. I have seen many students mistakenly list the angles alpha, beta, and gamma as the direction cosines themselves. Always remember, the direction cosines are the cosines of those angles, not the angles themselves. If you find an angle you aren't finished yet, you must take its cosine to find the actual value of L, M, or N. Second, do not ignore the directed nature of the line. Remember that a line extends in two opposite directions. If you decide to reverse the direction of your line, the angles change to their supplements, which means you subtract each angle from pi. This is crucial because it changes the signs of your direction cosines. For instance, if your original L value was positive, reversing the direction would make L become negative L. Finally, watch out for incorrect axis pairing. It sounds simple, but it is easy to get distracted during a calculation. Always ensure that alpha is paired with the x-axis, beta with the y-axis, and gamma with the z-axis. If you mix these up, you will end up describing a completely different orientation in 3D space. Keep these points in mind, and you will be well on your way to mastering direction cosines.